Please bring your homework 7 up if you haven't already. And just a reminder, there's another somewhat shorter, about the same length as this one, assignment due next Monday on Chapter 8. So that has been posted, and yeah, that's due a week from today. So we're going to work some more on Chapter 9 today. Chapter 9 is not too much longer. We should finish this up by Wednesday for sure. And then, yeah, after today we have exactly 6 lectures left. That's hard to believe. It's winding down already. But we have then one more full chapter, and then hopefully part of another chapter that we'll be able to cover here in this class. I think the things that we're getting to here in this later part of the class are things you'll definitely see later in your careers, one way or another. And chapter 12 and 13, which I'd like to cover, is talking about regression. And then that's chapter 12, and then we can do a slightly more advanced version of that, which I think you guys would also be able to use later in your careers. So that's sort of where we're going. I'll get chapter 12 notes are posted, and then chapter 13 that'll get up at some point in the next week here. Any questions or comments before we jump in this morning? No? Everybody good? Yes, sir.
Is this stuff that we're doing now, is that what's going to be in the final?
The final is everything since exam 2. So chapter 7 all the way to the end. Yeah. And so the final will probably be slightly longer than the other 2 exams, but you got the 2-hour period to work on that. So it won't be twice as long, but we do have a lot of material to cover on that exam. So yeah, chapter 7 all the way up through whatever we finish by the end of the semester. Yep. I think that final exam is Thursday morning or something like that. So just, I don't know if you're looking at that yet. Okay, well let's get back in here to chapter 9. Just remember now in chapter 9 we're kind of doing chapter 7 and 8 together, but in a new setting. We're looking at 2 samples. So in chapter 7 and 8 we were doing just 1 sample, confidence intervals and hypothesis tests. Here in chapter 9 we're doing 2 samples, and then we'll do confidence intervals and testing as well. So as sort of our starting out example here, we have, or sort of our basic assumptions that we have here, are that we have 2 random samples that are independent of each other. So we need our sample of x's to be independent of our sample of y's. And then each of those samples has its own mean and variance, mu1 sigma 1 squared, mu2 sigma 2 squared. And it is okay for us to have different sample sizes. That's not a problem. So in the first case that we looked at, section 9.1, we were looking at we're trying to estimate the difference in means between these 2 populations. So we want to estimate mu1 minus mu2. This is our difference in means. And kind of going back to what we were looking at in chapter 6, where, okay, if I want to estimate mu1 minus mu2, what can I use? And not surprisingly, we can use the difference in sample means, which gives us an unbiased estimator there. And then we can also derive what the standard deviation of that estimate is. And we walked through that on Friday. Okay, so again, here in sort of the simplest case, if we have some things that are maybe not that reasonable, but kind of to get the ball rolling here. If we start out with a normal population and we know what the sigma 1 and sigma 2 are, if we know what the variances or the standard deviations are, we talked about how to do a hypothesis test for this setting previously, but now we can also write down a formula for what the confidence interval is. So remember, our general form here is we have an estimate plus or minus a margin of error where the margin of error is equal to a critical value times the standard deviation. So it's kind of the exact same setup as we've always had. We're just putting in, now our estimate is something different, it's x bar minus y bar, and we're also putting in the appropriate standard deviation here. So we're putting in the standard deviation of our estimate. Okay, so again, if I want a 100 times 1 minus alpha % confidence interval, there's my formula. All I need to do is figure out a particular critical value, figure out what that is. if I want 95%, the Z value, remember, is 1.96. Then we had some of those other standard levels that we looked at. So this is kind of getting back into some more familiar territory, I would think. But then again, just sort of here we're assuming that we know what the sigma squareds are. And so we know everything in this formula, and we can calculate that and give a confidence interval. So applying this here in our Duracell versus Energizer battery example that we did a test for earlier, let's now create a 95% confidence interval for this difference in average lifetimes. Okay, so again, we want to estimate mu1 minus mu2, which is the difference in average lifetime, and this was make sure I have this correct. So this was Duracell minus Energizer. Okay, and again, we'll just make a note here, we already checked our conditions, so we're going to kind of skip over that now. So we already checked conditions when we did the first part of this example. So we can jump right in and actually do our calculation here. So again, our confidence interval here is x bar minus y bar plus or minus z of alpha over 2. Times big square root here, sigma 1 squared over m plus sigma 2 squared over n. Okay, and we have all this information. So x bar was 4.1, y bar was 4.5, plus or minus our critical value times big square root. First variance was 1.8 squared. We had 100 in both of our samples. The other variance was 2.1 squared, or sorry, 2 squared. Okay, so I just need to plug in what my critical value is here. What's my z alpha over 2? I want a 95% confidence interval. 1.96. There we go. And we're done. So calculate this out. This is negative 0.927 all the way up to 0.127. Okay, let me write that down, 0.927 up to 0.127. Okay, so this is our confidence interval for that difference in mean. Let's say exactly what we mean by that. So here we can say we are, same setup here, we are 95% confident that the true difference in mean, true difference in average lifetimes and now again, we can write down the same interpretation, but now that we're talking about two populations, two samples, it's a little bit more complicated. So we're saying that the true difference in average lifetime for the batteries. Let me write down. We're talking about Duracell minus Energizer. And then we can say what we mean. So it's between 0.927, and what are our units here? Hours less. to 0.127 hours more. Okay, so we're 95% confident that this true difference in mean between these lifetime batteries is between almost 1 hour less than 0 or 0.127 hours more for the Duracell battery. Okay, so when you have two populations, be a little careful about make sure you know which one is what your order of subtraction is there. Okay, yeah.
Okay, you just said the difference, and then you clarified something on something is between negative 0.927 and positive 0.927.
Yeah, question was, so can you just say 95% confident that the difference between, and then kind of say what you're talking about. So first group minus second group is between negative 0.9, yeah, that's fine too. Put between negative 0.927 and positive 1.127. That's okay. Okay, so does this agree with our hypothesis test? So if you remember from previous page of notes, we did a test and we failed to reject the null hypothesis, which was that mu1 minus mu2 is equal to 0. So does this agree with, does our confidence interval agree with the hypothesis test? So we failed to reject our null hypothesis that the difference was 0. So does this confidence interval agree with that? Hopefully it should. Yes, right? Why does it agree with our conclusion there from the hypothesis test?
The middle is more negative.
Say again?
The middle is more negative.
The middle is more negative? The middle of the confidence interval?
The zero is inside. Yeah. If you took the median, it would be a negative value.
But we failed to reject that hypothesis.
It's just because zero is inside the confidence interval.
Yeah, so remember there is this sort of duality between confidence intervals and hypothesis tests. When we first talked about this, we thought about we did it the other way around, right? First we did a confidence interval and then we did a hypothesis test. And so that's sort of an equivalent way of doing the test is to see if that number, the hypothesized value up here, falls within the confidence interval. And so here 0 is inside the confidence interval. We're saying this difference could be either positive or negative, so we can't say that it's significantly different than 0, or significantly less than 0 even. Even though, as Jamie said, our sample mean, x bar minus y bar, was less than 0. So our sample data told us that indeed there was a difference, but again, the point of the hypothesis test here is that a significant difference? Is that different enough, given sampling variability that we might find, is that different enough to say that there is actually a difference? And our hypothesis test said there wasn't, and here our confidence interval is saying the same thing because 0 is in there. We're estimating that this difference in means might possibly be equal to 0. So, the confidence interval estimates that mu1 minus mu2 might equal 0. So again, remember we're giving an estimate for that parameter mu1 minus mu2, and if I'm saying it could be equal to 0, then that's kind of telling me the same thing that my hypothesis test told me. Okay, so that's a very, very important connection there between testing and confidence intervals. Is that okay with everybody? Okay. All right. So maybe right before I move on, suppose that I had switched the labels on my sample here. So what if I had let X represent, or my first sample represent Energizer, and my second sample represent Duracell? Is that okay? Is there a problem there? If I switched the labels on my samples, so if I said the X samples were actually Energizer and the Y was actually Duracell. Exactly right. Yep. So it doesn't. So if you had done it that way, your confidence interval would just have been, negative 0.127 up to positive 0.927, and your your alternative hypothesis would have switched directions, so your p-value would have been the same. All your conclusions are going to be exactly the same. So it doesn't matter, is the point, what order you list your groups in there. If X or Y could be either group. Again, just the important thing is your interpretation. So either setting up your alternative hypothesis, making sure the inequality is going in the correct way, and then also saying here for your interpretation which group is which. So it doesn't matter which group you call which thing, but just make sure your interpretations are all clear. Okay, so that's sort of the setup for when we have normal populations and we know what variances are. So now we're going to kind of move into looking at both of those assumptions, as they are not always going to be appropriate. So kind of backing off the condition that we know what the variances are. So when we do a two-sample t inference, now we can say we don't know what these variances are. But we still sort of have the same setup. So we still have normal populations, and we still have random samples, and our two samples are independent of each other. We can do the exact same thing as we've done before. So we're still looking at mu1 minus mu2. Hypotheses are as before. So mu1 minus mu2 equals some delta. So and then your alternative is the same thing, but just with a not equal to, a greater than or less than delta 0. So our hypotheses are still the same. We're still interested in testing the same type of question. And again, we observe independent random samples from each of our populations. So x1 up to xm, are IID normal. And the y's are IID normal as well. It's a different mean and different variance. Okay. But now also sigma 1 squared and sigma 2 squared are unknown. Okay, so same type of setup that we've been looking at all along here. Okay, so our test statistic then changes exactly like you would think it would. Before it was a z, which was x bar minus y bar minus delta 0 over. Remember, we had sigma 1 squared over m plus sigma 2 squared over n. And so just like we did before, if I don't know what sigma is, sigma squared 1 and sigma squared 2 are, well, I'm going to estimate those with my sample variances here. So here's our sample variances. Okay. And when the null hypothesis is true, again, this is going to have a t distribution. So kind of seeing the same thing that we've seen before. So a formal statement of that here is as long as my population distributions are normal, and I have random samples and the samples are independent, and when the null hypothesis is true, then this thing has a t distribution with degrees of freedom equal to this messy formula. So again, before we just took n minus 1. Well, we have to do a slight correction for that degrees of freedom here. When we do a two-sample test for means, when we use the t distribution, just sort of the theory, this is how that works out. So when you're calculating degrees of freedom, this is now your degrees of freedom that we'll use. So we calculate it based on the sample variances and our different sample sizes. Okay. So it's a little messy, but we can definitely deal with that. And so then when we actually observe information, we'll calculate our test statistic, and we can use that to make our conclusions. So we'll calculate p-values. And make conclusions as in reject versus failing to reject as before, so same as we've been doing all along here, except we now have a different degrees of freedom. So except our degrees of freedom is now, we use the formula for mu, which has the formula on the previous page. Okay, so again, we're doing the same thing that we've done all along. You'll calculate your p-value. You'll just use a slightly different degrees of freedom here now. And then you'll use your p-value, compare that to your significance level, reject, fail to reject, and then make a conclusion there. Okay? Yes, sir?
The degrees of freedom formula, that's for, it says when the null hypothesis is true. If it's false, we still use the formula too.
So this is degrees of freedom when the null hypothesis is true. When the null hypothesis is false, can you still use this formula? So we're only using this degrees of freedom here to calculate our p-value, right? And so that's only under the case that the null hypothesis is true.
Okay.
So you only need to worry about the degrees of freedom in this formula. I mean, sort of all along you start out by assuming the null hypothesis is true, and kind of make your calculations based on that, and then see, is my p-value small or big? Is the null hypothesis true or not true?
Okay.
So you don't need to worry about the case when the alternative hypothesis, when the null hypothesis is false. You don't need to worry about that. Okay. Other questions? Well, we can use the same thing to calculate a confidence interval. So again, same setup. If I have independent random samples from two populations, then my confidence interval is exactly what you would expect it to be. So formula, again, we have our estimate plus or minus our margin of error. And again, the only difference here is that our critical value is now a t with new degrees of freedom. So with Greek letter new degrees of freedom. And we'll calculate that just like we did before. So that will hold up there as well. Okay, so instead of going through this whole song and dance one more time, we can just jump to this. So that everything that we just said was assuming that we had a normal population, right? So x1 up to xm were IID normal, y1 up to yn were IID normal. What happens if I don't have a normal population? Are all these formulas completely useless? Of course not. Mm-hmm. Absolutely. So we're going to do the same thing that we've been doing all along here. So we're going to use the central limit theorem. Okay. So if I don't have a normal population, if I don't want to assume that about my population, I'm going to do everything the same. Except I need to check something. What do you think I need to check here? My initial conditions, yes. So I definitely need to have, again, we're still assuming I have random samples that are independent of each other. So then what's the other condition that I need to, how can I use the central limit theorem? When does that kick in? Yeah. Yes, exactly right. So I want to check something about my sample sizes, make sure they're large enough. So I want to make sure n is bigger than 30. But I have two samples now, right? I have n is the number of samples from my y distribution, but I also need to check that both of my samples are bigger than 30. So when this is true, when this is satisfied, the t-test and interval will give good results. Kind of, they will be appropriate to use here. They'll be appropriate to use here for this setting as well. So as long as your sample sizes are big enough, the same formulas for the testing, for the hypothesis test and confidence interval will be good to use here as well. So even if I don't have a normal population, you can fall back on sort of the same things that we've been looking at all along here. Okay, let's do a few examples here then. So suppose now that I have mu1 and mu2 are the true average stopping distances starting at 50 miles an hour for cars equipped with a certain type of braking system. So I have two different braking systems here, and I want to know the true stopping distance for each of these braking systems. Bless you. And so then I'm going to use the so what I want to do here is I want to test this difference. So I want to test this at a significance level of 0.01 to test the null hypothesis that the difference is -10 versus it's less than -10. Okay, so my null hypothesis says that the difference is negative, so that so under that null hypothesis, what am I hypothesizing? Which braking system is better? I think I heard both mu1 and mu2. So this says that mu2, if their difference is negative, that means mu2 is bigger, right? But if I'm looking at a stopping distance, I probably want that stopping distance to be shorter, right? So that means mu1 is maybe better here. So just kind of remembering what it is we're talking about. Versus the alternative says that this difference, that mu1 is actually much better. It's more than a 10. Doesn't say what units I'm using here. Maybe we'll talk about meters here. Okay. Anyway, I want to test these two hypotheses using this information that I have. So I have six observations of my first braking system, which gives me an average stopping distance of 115.7. I have 6 observations on my second one, which gives me an average stopping distance of 129.3. And I have my sample standard deviations here as well. Okay, so let's see what we need to do here. So wrote down my hypotheses. I know what those are. What's my next step, or how do I proceed here?
Calculate your test statistic.
Yes. So I'm going to calculate my test statistic, but I need to kind of figure out, what do I need to figure out before I calculate my test statistic? Degrees of freedom. So yes, I also need to calculate that. Before I start doing any calculations, though. So I need to, well, first of all, we need to figure out which procedure to use, right? We're going to do a t-test here. But then what do I need? I want to make sure that it's okay to use a t-test here, right? So I don't want to just start blindly applying my calculations. I want to make sure that it's okay to use a t-test here. So is it appropriate to use the t-test? Okay, so how do I know if it's appropriate to use the t-test? What conditions do I need about my... First of all, what do I need to know about my samples? I need them to be random, right? I need a random sample from both populations. And what else about them? What do I need about the samples? I need them to be normal and also independent of each other. So I need random samples, random independent samples, and I need normal populations or large enough samples. So that second thing is that difference that we just talked about. So if I have normal populations, I don't care what my sample size is. If I don't have normal populations, then I need my sample size to be large enough. I need it to be bigger than, both of them to be bigger than 30. Okay, so we don't have any of this information here. We don't know what the population distribution is. We don't know how we've gotten these samples. So I guess just the point is that in order to proceed and use these calculations, we have to assume both of these things. So we have to assume that we have random independent samples, and we have to assume that our populations are normal because our samples are not large enough, right? N equals 6 and M equals 6. So in order to use this, we need normal populations and independent random samples. Okay, so again, I don't know enough about stopping distances to know if a normal distribution is appropriate. That's where we'd go talk to our expert engineer maybe in that case. Does anybody know what kind of distribution the stopping distance might have?
It would depend on if you're using the same break every single time, because then it would wear down, so it probably wouldn't.
Oh yeah. So it would depend if you're using the same brake every time. So I think here we have maybe like 6 different cars all with the same braking system. So hopefully we have the same. Hopefully we're using a different braking system to kind of truly test this stopping distance. So we're gonna go ahead and do our test anyway, but just kind of keeping in mind that in order for our results to be good, we sort of need, this is what we need to be true. So some assumptions that we would want to maybe get a little bit more information on if we were actually doing this test here. Okay. So assuming that we can move forward here, we need to next calculate our degrees of freedom. So nu equals this big messy formula, sample variance 1 plus the second sample variance over n squared divided by s1 squared over m squared over m minus 1 over n minus 1. Okay, so this is, if you plug in the information that we have, first sample variance was 5.03 squared plus 5.38 squared over 6, all that squared. .38 squared over 6 squared over 5. Okay, and if you work that out, you'll get 9.9956. Okay, so we do that giant calculation, we get that. So that what that means is we want to round down, so we're going to use degrees of freedom equal to 9. So even though all of your training is telling you to round that up to 10, for this we want to round our degrees of freedom down to 9. Okay, so we're now ready to find our test statistic here. Our test statistic here is again x bar minus y bar minus delta 0 over s1 squared over m plus s2 squared over n. Okay, so x bar here was 115.7 minus y bar, which is 129.3, And then the hypothesized difference there, so from our null hypothesis we had a negative 10. This is from the null hypothesis. And we're going to divide by our standard deviation. Okay, if you work all that out, you will get negative 1.2. Okay. So our test statistic t is negative 1.2. Have my test statistic. What do I need to do now? What's my next step? So my next step is always test statistic, and then what do I calculate? P-value, absolutely. So my p-value is going to be the probability that a t random variable with the right degrees of freedom, and then I'm going to have 1.2 in there. What's my inequality symbol in there? Less than, right? Because my alternative hypothesis was a less than in there, so it's less than in my p-value calculation. And yeah, now I'll go to my table. Again, I'm using my degrees of freedom are 9 here, so I can look up what my p-value is. So what the table tells you, this is going to be the same as the other tail probability. So both of those tail probabilities are the same, and from the table you can find that that is 0.13. This is from the table. Okay, so there's my p-value. Time to make a conclusion. What am I gonna do here? Reject or fail to reject? Fail to reject. Why is that? Yeah, so my p-value is pretty big. We actually want to use alpha equal 0.01. So either way, you're going to fail to reject. So your p-value is bigger than alpha here, which is 0.01, so we fail to reject. Okay? So what that means here is that, again, my usual interpretation, there is not sufficient evidence to conclude, and then say what the alternative hypothesis says here. So what the alternative says is that the difference in means, the difference in average braking, in true average braking distance, is less than negative 10. And here we're talking about braking system 1 minus braking system 2. So didn't say what those two things are, but just we're taking the first group minus the second group there. Okay, so there our p-value is large, bigger than alpha, so we failed to reject, which means that there is not sufficient evidence to conclude that the difference in true average braking distance is less than negative 10. Okay, so this is probably hopefully this is starting to feel comfortable by now. I don't think this is anything too crazy. It's kind of extending our methods to two sample situations here. Questions, comments? Okay. So one more example here before we wrap up this section 9.3. Let's look at an example involving lower back pain. So this is a serious health problem, obviously in many industrial settings. And we have an article that reported this data here on lateral range of motion for a random sample of workers without a history of lower back pain and another sample with a history of lower back pain. So we have our sample sizes, we have our sample means, and our sample standard deviations there. Okay, so keeping your eye on that data here, we want to calculate a 90% confidence interval for the difference between sort of the lateral motion that each of these groups have, and then does this interval suggest that the population mean is different under these two conditions, so that somehow lower back pain impacts your lateral motion. Okay, so first step for these things, let's write down what our parameters are and what we're interested in estimating here. So let's let mu1 equal the average lateral range for workers without lower back pain. So let's let that be our first group. And let's let mu2 equal the average lateral range for workers with lower back pain. Okay, and the first thing we want to do is calculate a confidence interval here. So we want to calculate a 90% confidence interval. Okay, so again, to be able to use this confidence interval, I need to have random samples that are independent of each other, and then I either need normal populations or my sample sizes to be big enough. So how am I doing with my random samples? Yep, stated. So I have random samples. I need them to be independent samples. So are my samples independent here? Do the people with lower back pain, do those people that I have in there have anything to do with the people without lower back pain? So there's sort of no reason to expect that you'd have like siblings or something in these groups, or some reason for dependence. So I think it's safe to say that we have samples that are independent of each other. And do I have normal populations here? Do I know anything about my populations? No, I don't. So then I need to make sure that I have large enough. So n was, or m is 28, and n is 31. So n is bigger than 30. 28 is not bigger than 30, but it's close enough. So we don't have to be exactly 30. This is close enough. Again, splitting hairs there if you're getting that picky. So we're going to say that we're good to go with our large enough conditions here as well. So if you start getting down to like 25 or 20, then you're probably not close enough. But 28, that's fine. Okay, so we are in fact able to use our formulas here. So let's jump in here. So the other thing I need here is my degrees of freedom. So this here is using my sample statistics, 5.5 squared over 28. 7.8 squared over 31. Over 27 plus over m minus 1, which is, or n minus 1 rather, which is 30. And if you calculate that out, you'll get, what will you get? 53.96. Okay, so we can use degrees of freedom equal to 53. Okay. So now we're ready to calculate our confidence interval. This is what do we have here? So again, alpha equals we want a 90%. Well, let me write this down. We have a 90%, which means that our alpha is 0.1. So our critical value t, our degrees of freedom are 53 here. And alpha over 2 is 0.05. So from the table, that's going to be approximately 1.676. So this is from that critical value table that we were looking at before. Okay. So then our formula here is, again, x bar minus y bar plus or minus our t critical value times this times our estimated standard deviation here, S1 squared over m. And so the difference in sample means we had 91.5 minus 88.3 plus or minus 1.676 times 5.5 squared over 28, 7.8 squared over 31, which is equal to 0.276 up to 6.124. Okay, so remember this is a confidence interval for the without lower back pain minus with lower back pain. Okay? And we're talking about our units here, we're talking about the lateral range of motion in degrees. So let's interpret this thing here. So we are 90% confident that the the true difference in lateral range motion again in degrees is between 0.276 and 6.124 degrees more for the group without lower back pain. Okay, so we're 90% confident that the true difference in average in lateral range motion in degrees. So we're talking about the without lower back pain minus the with lower back pain. So that means the without group is larger since our confidence interval is positive. So we're saying that it's between 0.276 and 6.124 degrees more for the group without lower back pain. Okay, so again with these two samples, your interpretations need to be a little bit careful about how you say that exactly, but just make sure you have your groups in the right order there. Okay, questions or comments? Is everyone okay here?
So then that does suggest a difference, right?
Yes, right. So then we do want to go back and also ask, does the interval suggest that the population mean differs for the two conditions? So, Dan, you say, yes, that does suggest. And why does that suggest? That the means are different?
Because zeros make it.
Yeah, exactly right. So, yes, this does suggest a difference in population means, because 0 is not in the interval. So yes, this does suggest a difference in our population mean, because our estimate for what that difference is does not include 0. So we could formally do a hypothesis test, but you would get the same conclusion there. And so then, if you sort of, without doing the hypothesis test, what significance level have you used here? Or what significance level does your test sort of hold up here? So it's whatever alpha was, right? So our confidence interval, which didn't include 0, was a 90% confidence interval. So that means our significance level is what? 0.1, yeah. So this means that alpha equals 0.1. So your conclusion to sort of reject the null hypothesis in some sense, if you set it up that way, would be valid at a significance level of 0.1, just to kind of keep that straight. Because if you calculated a 95% confidence interval, that thing might in fact include 0. So just to keep that in mind. Okay, I think this is a good place to stop. We'll let you guys out a few minutes early. Have a good rest of the day. We'll see you guys on Wednesday.